Good morning. Let's start. Although half of them will come in like 5 minutes and make loud noises. Okay, so we start today with neurocognitive methods. So the topic today is the MR signal equation. And to get started, let's briefly review where we went up to. So we actually discussed. Can you close the door? Thanks. We discussed the dynamics of a magnetic moment vector in 3D, and essentially we went up to. If you remember this kind of picture, I cannot really draw it nicely, but this is essentially what came out of it. So this precessing movement with an exponential decay along the z direction, and this kind of movement after excitation is described by this set of differential equations. And last time we worked or we checked that some equations can be considered the solutions to this, and let's start there again. So what we discussed, or what we actually found, is the following set of solutions. So we have our components, and they are functions of time and space. For the moment I just write the time variable here, and they are given by an exponential decay. This is what we discussed last time, which is governed by a time constant T2, which describes how fast this decay here towards the Z happens. And this exponential decay is then multiplied by the initial conditions of the original magnetization, which is this extent that at time 0 the magnetization vector actually extends. So that's essentially kind of this arrow length. And then this is multiplied by a cosine term of some frequency, and this frequency is time dependent, and in a second I will discuss what this time dependence was. But first let's write out the full thing. Plus my sine, now we're hitting this, sine omega t. So that was the bracket missing here. The x dynamics, the y dynamics are fairly similar, so they again are this exponential decay, and then it's essentially the same thing, but with a minus here, minus mx sine omega t. And in the z component we just have an exponential decay, which is governed by the time constant t1. Yeah. Now what this describes, again, especially if you only look at the x and y plane, so if you look at the whole thing from above and basically project out the z dimension, so if we have x and y here, then at time 0 you have some magnetic moment vector pointing outwards. And do you remember what this length of the magnetic moment vector at time 0 depends on? From your general Hüttel knowledge? Well, this depends on the strength of the magnetization at this location and time, because remember, at equilibrium, you have some equilibrium magnetization that is due to the fact that all the spins, so the nuclear components that build up this net magnetization align with the magnetic field and become a magnet themselves. And this is at equilibrium pointing in the z direction. And then by excitation, it's tilted into the xy plane. Remember that? That was kind of what we discussed very early on in autumn. And the length of this depends on the strength of the magnetization at this location and time, first in the z direction, and then it's tilted into the xy plane, and this is our time 0. So at time 0 we have some magnetization that corresponds to the equilibrium magnetization, and then this magnetization starts to move. So it's forming a circular movement and it's reducing in size. So so after some time it looks like this, and then it looks like this, and then it looks like this. If it's doing this kind of movement, so you get this picture that we also looked at that looks something like that. Yeah. And this thing is described. This is exactly this. Yeah? So the x and y, these equations, so the exponential decay means that that the length of this vector in the xy plane is reducing over time, and how fast it reduces depends on t2, and the cos and sine terms just describe this spiraling movement. This is what this describes, and the question is at what frequency this is happening. So there's this omega t term, which is my summary notation for this. So omega 0t. What is omega 0? I think you're confusing it. Yes. So omega 0, what's it's called and how is it defined? And how is it defined?
It is the gamma times the P0.
And what are gamma and P0?
P0 is the net.
No.
In the z direction.
In the z direction, but what is it? You're practicing the oral exam.
Yeah.
Which magnetic field? The static magnetic field. So that's the strong magnetic field that is the reason why you shouldn't wear any metal when you go into the scanner, because this will draw you in. And what was gamma?
I remember the Lambda frequency was the frequency at which the spin was like the perfect frequency.
Yeah, this is the good thing about mathematical things. You don't have to memorize them. You just have to understand them. That doesn't work. So the thing is, also this kind of stuff you just have to memorize, because what is there to understand if you don't memorize it? So anyone remember what the gamma was?
I don't know if I'm right, but isn't it for the specific molecule of proton you want to measure the spin of that?
Yeah. Yeah, so essentially what it describes, so you can see it as a proportionality constant. So this spinning movement, so the frequency at which the precession is happening in the absence of any other magnetic field, is dependent on the nucleus that you look at, and it's proportional to the B0 field. And so basically you can observe some spinning at a frequency omega 0, and this frequency omega 0 depends on the specific nucleus. So gamma is the gyromagnetic nucleus, gyromagnetic ratio, which is dependent on the nucleus. So it's the proportionality constant for the frequency of precession. So that's depending on what you're trying to measure, and the B0 is given by the building by the structure of the scanner. So that's the strong magnetic field. So that was kind of what's always happening. The other thing is that we also now look at what I refer to as the B2 field, which is, as we also looked at last time, in the solution form given by this function here. Does anyone remember what this delta B is about? Yeah, so they, so it's the gradient fields, or let's say it's a mathematical model of the gradient fields, because clearly this is not a gradient coil, but this is a delta B R tau notation on a digital thing, a Windows surface. So it's not a gradient coil, but it models the gradients, and these gradients are time or let's say it's better. So the gradient coils are allowed to induce variations of the magnetic field in the scanner, and these variations are space and time dependent, depending on how essentially when these gradient coils are turned on and off, and how much they are turned on and off. And what this describes is the temporal integral of this additional magnetic fields that are induced by the gradient coils at a specific location. So actually, because I didn't have the location up there, it would make more sense to also not put the location at this point in here. So then it would, for one location in space, be just the temporal integral of the changing magnetic field that is superimposed onto the static magnetic field. So basically, when we looked at this thing last time, and from this perspective, this was set to 0, and how fast this inward spiraling movement takes place is then just a function of the Larmor frequency. Good. So this equation here, so the z component is the buildup in the z direction. We will now actually, essentially omit further consideration of the z component for some time, essentially until we have finally figured out how an image is formed. Because this is interesting from the perspective of the sequence parameters in terms of TR and so on for measuring T1 time constant differences, but for the image formation it's not relevant. Do you remember why?
Because this kind of is built just to measure the signal in the XY plane.
Exactly. So that's the engineering constraint there. So for basically from now on, for at least today's session, and then I guess also when we talk about 2D Fourier next session, we will essentially omit this Z part. So then we are essentially now looking at the following. So we have for one location in space now discussed the dynamics of a magnetization vector which does something like this. Yeah, so that's our mx and my as a function of time. And now we need to do two things. First of all, we need to re-express our solution in terms of complex exponentials, because that's just the standard language that is used, and we have to consider what happens with respect to space. So let's start with the intuitive idea. So what we have seen so far, let's call that now mxy over t, and this is our 2D vector. So this is an mxy over t, so a 2D entity that shows this kind of movement. Now the thing is, that was all at one location in space. Yeah, so we didn't really talk about the R, but it was from the beginning clear that this happens at one location in space. So at one R, where our R is the XYZ coordinate of this magnetization. Now the thing is that what this describes is, if you want a magnetic moment located at the location X, Y, and Z, and at this location, so M, R, T, at this location R, it does this. Now the thing is, we are of course interested in spatial properties of our samples. After all, we're trying to make a spatial picture of the sample. So what we described so far for one location, of course, is conceived as a function over space. So if you imagine this now from a discrete perspective, then at one location in space, you have this, and at another location in space you have, it's not moving differently, it's of course doing the same thing, inward spiraling. You have this. At another location in space it's doing this. At another location in space it's doing this. And so you have these things all over your sample. So let me make this maybe a little bit clearer. So if I'm drawing more, I hope this helps. So these little, can't really draw them. Can I draw them? So these things here, they are all these inward spiraling things, and they now become explicitly distributed over space. So you have an X component, a Y component, an X and Y location, I should say. So don't confuse that with the X and Y component, X, Y, Z components of the magnetization, but see this as the X, Y, Z, and more importantly the X, Y dynamics at different locations in space, so as a function of space. So you have this, and then of course you also have this in the Z dimension. So you have, if you want, you have pages of this. It's a little bit hard to, maybe I can try with gray to put in 3D one behind that. So this is now Necker-cubish, trying to visualize that this happens in 3D. Yeah. So the way you should view this is that this function m x y r t, that these different locations, they are different r's. Yeah? So you can, if you want, you can label them r1, r2, r3, r4, r5. And then for each of these r's, so for each location in the sample, you have one magnetic moment that does this evolution. Yeah, do you get what I'm getting at? So you can view this essentially, if you want, you can of course view each magnetic moment as a little magnet. Yeah, so maybe let's try this again. So a magnet, that's a magnet with a north and a south pole, like the ones that you played with, and these magnets are spinning and form this inward spiraling movement, so they essentially reduce their magnetization over time. That's kind of the idea. And these magnets are located at each location of your sample. Yeah, so you have, because this is of course this is a continuous function, you essentially have an infinity of little magnets that form this movement, and these magnets are located at each location in your sample. Yeah. So the important thing is that you realize that there are that basically this x, y, z comes in twice. So x, y, z first fixes the location of your magnet that does this, and then your magnet evolves in x, y, and z, and we for this evolution we disregard the z dimension. Yeah, so we only look at the x, y component, because this is what is measured. Yeah, I'm not clear whether that's clear, but to me it's clear. So if it's not clear to you, please ask. Good. This was already there, so this is essentially, this is not really novel, this is just a picture that basically gives some intuition to this dependency on space. And of course the idea is that at different locations in space, this happens slightly different. Yeah, all of them form this inward spiraling movement, but maybe they start out from a smaller vector, or they do it faster depending on the T2 value. This was why T2 was space dependent. This starting out from different values would be that the initial conditions, so the net magnetization at equilibrium would be different. So they all do qualitatively the same inward spiraling movement, but quantitatively this might sometimes happen faster or with a smaller amplitude. Now, what the MR system then measures is actually not the individual magnetic moment at a specific location, but the spatial integral of all these dynamics. So let's continue with that. So again, and we are now continuing actually at the MR signal equation. So we are concerned with the XY projection of our magnetic moment at location R, as we just discussed. And now the signal that is measured by the receive coil of the MR scanner is, or can be described as follows. It is time dependent. Yeah, so the receive coil measures a signal at time 0, so that's excitation, and then for the time following excitation. It's two-dimensional, so the signal that is measured consists of two numbers, and what this signal refers to is the spatial integral of this XY projection of the magnetic moments. where the integration is over the entire sample or space, or however you want to see it. So this is a three-dimensional integral. The way you should think about that is as follows. If you think again about the integral of a function in 1D. So let's say you compute the integral from over, so this is now x, so it's not, so we are talking about the integration over space here, yeah, so it's a spatial integration. If you compute the integral here over the x domain, what do you get? So let's say you compute the integral from here to here, and that's why I wanted to put something there. What is the integral? Not in terms of numbers, but in terms of intuition. The area, exactly. And how many numbers is the area? 1, exactly. So you get this area, which is a real number. Let's say, in this case, depending on what the, let's say this is 1, and this is also 1, then this is roughly 1/2, roughly, because it's kind of what is covered. Remember again that the integral is kind of an average, so or it's essentially, you should think about it as an average. So if you compute the integral of something like this, what do you get? 0, yeah, because this is a sign, so this is positive, this part, and this is negative, so you get roughly 0 for this. Now we are dealing here with a 3D integral. So first let's think of a 2D integral. So in 2D, of course, you can have a function, and then you can compute an integral over space. So this was x, so this was fx, and this was also fx, and here fxy would be now encoded, let's say, with some colors, so that red means a high value, so something like this, so that's a high value, and this is a little bit less of a value. And if you compute the integral over y and x, or x and y, of this function over some domain, let's also call this already, let's say S, then you again get one number that corresponds to the average of the function fxy over this space. Yeah, so this integral here over S of the function fxy, where you can write, for example, dx and dy, is also just a number. Yeah, and then, of course, similar for 3D, which is hard to visualize. So the way you have to visualize, or you think about it, is that you're essentially going through some space, like this room, and this room is filled with I don't know, something. It's filled with something that has a color, and if you are, let's say, at the edges of the room, then this color is kind of orange, and then you go further through and towards the middle. So if this is basically reflecting what I've just drawn here to the middle, it gets red, and these colors represent the function fxy in fxyz in a 3D space, and the integral, so this kind of space integral here, then is the average of all these function values throughout 3D space. Yeah, it's not easy to visualize, because one way to visualize is that if this is for one z location, so let's say that this is at z1, and then you could draw another slice at z2, and the integral that is meant here over space means over the average over all 3 dimensions of space. questions about this?
So if this integral down there with the dx, d epsilon, dy, sorry, what would be, how would it be interpreted if it would, if it just would be a partial integral, for example, dx, only dx? What would that mean?
That would mean that this is actually also what's happening here. That would mean if you have a 2D function, which so a multivariate function that you integrate only with respect to one variable, then what you get out is, of course, a function of y, which is defined as the integral of 2D function over x.
So this is x integrated out.
Yeah.
What does the, and I don't really get what that means, what this integral, why does it vanish? Like, I don't know.
Because you, no, it vanishes because, it vanishes like it vanishes here if you compute the average of this function over this kind of space. So here you have f of x is a f is a function of x, and now you can simply do this as you sum all the values of f for all x. So you do, so if you would have this discrete, then it's of course easier. Then you would do fx1 plus fx2 plus fx3. And so on. So you form the average, and then you just get out one number. So in this sense, the dependency on space goes away because you average the values over space. So if you want that even in a different way, so if you have normally this dependence on space, something like this, let's do kind of a linear function. No, it's not linear, it's linear fine because it it's not 0 at 0. Then if you now sum all of these values, so minus 1 plus 0 plus 1, that's 0, plus 2, that's 2, plus 3, it's 5. So your integral or your sum over the fxi here from I, we can do like this, to 5 is just, what did I say, 5, so it's just a number. So it vanishes because you forget the dependency on space and you look at the average. I mean, it's the same thing as participants. If you compute, if you have 10 participants, and then for each of them you have a measure like their height, and then you compute their average, then you get, I don't know, 1.7 meters. And now the dependency on the individual participant has vanished because you just compute the average. Right? And what happens in our case with the MR signal equation is that the dependency on space vanishes. The dependency on space is here three-dimensional, but this is just basically averaging over all three dimensions of space. What does not vanish is the dependency on time, and this is exactly like here where you integrate with respect to one variable but not the other. Yeah, so for each point in time you look at the average magnetization in the xy plane over space at a given point in time.
But if we don't have that dependency on space,
how do we make a picture? Yeah, and that's exactly the point. So this is what we will go on. But this is a very important point. Yeah. So the thing is, the sample is somehow emitting this magnetization, and the scanner, so the receive coil, has no, in its signal that it receives, it doesn't have kind of a way to say, okay, at this location in space it was that much, at this location in space it was this much. So that would I don't know. I mean, there are different ways to look at it from the perspective of trying to measure neural activity. So if you have an electrode for each neuron, then you can say, okay, this neuron did this neuron did this neuron did this. if you just have an electrode that you put on top of the scalp and measure the summed activity of all neurons, then of course you just have a summary measure, an average measure over space, and you cannot say which cell did what. However, although this is the signal that is acquired, it's possible to create images, hence MR imaging, and this is done, of course, via a Fourier analysis. This is what we discussed Fourier analysis beforehand, and how this works from this summary measure. This is still what we need to discuss. I mean, we haven't done that yet. Yeah. But yeah, so the important thing is that the signal equation, or that the signal that is acquired, so that's the MR signal, is the average of, so the MR signal first of all is time dependent, so it's a function of time, and it's the spatial average of all magnetizations projected into the XY plane at a given time. And so spatial average and time dependent. So it's a dependent, and it's actually a 2D signal. So there are two numbers acquired at each moment in time by the MR signal, by the receive coil of the MR imaging system, but these refer to the bulk, if you can say it like this, the bulk magnetization of the entire sample, how that evolves, or how large that is at a given moment in time. Now, of course, we know what MXY R T is at a given moment in time, because we computed the solution for that. However, if one wants to basically use this logic for 2D Fourier imaging, it is helpful to rewrite our solution, as I said earlier, in complex exponential form. And this then looks as follows. So we have our MXY T, RT I should do now, RT, which is our MX RT MY RT, as we discussed last time and today a couple of times. And this can be written as follows, and I think in the next, after the break, we will discuss how that works, but I'm first giving you the solution. So this is rewritten in complex exponential form with a number of things that I still will have to introduce. So we see again our exponential term, and then we have an exponential term with the complex number, or the complex unit, so I, omega 0, that's our Larmor frequency T, and a complex exponential term with our gradient form. And the idea is that where this comes from, we will discuss in the next hour. But the idea is that the MCRT is our MX that we had already, plus I, so again I square root minus 1, RT, and our little MC RT refers to the initial condition, so that's given by our MX R plus I M Y M R. So that if you remember the real and imaginary parts of complex numbers, if you look at the real part of MCRT, what is this? What is the real part of MCRT? Exactly, so that's our MX RT, and what is the complex part? Sorry, they're not the complex, the imaginary part, that's how it's called. Exactly, that's our MY. And the same for the initial conditions, so our MC, that's not a function of time actually, that's wrong because it's the initial condition, it's just a function of space. That's our MX R, and our imaginary part of MC R is our MY. So again, this is a little bit like the three forms of writing the precession in terms of the cross product form, the differential equation form, and the solution form. It's the same thing. It's always this spiraling movement. This description in terms of a 2D vector, so in terms of this vector, or in terms of a complex number with a real part and imaginary part, is the same thing. It's just this is, if you remember when we talked about complex numbers fairly early on, I established something that essentially you can point in 2D, you can either write as x, y, that's a 2D point, or you can say, okay, this is a complex number, namely the complex number x plus I, y. Then the real part, then this denotes the real part of the complex number z, and this denotes the imaginary part of the complex number z. So in very straightforward terms, this just corresponds to a relabeling of the axis. And let me show you before the break the picture. So we're looking at the XY projection of the whole thing, and we discussed, of course, this for some time. So MXRT, it's this inward spiraling movement, and you have the X and the Y. Thanks. Actually, I now finally bought it myself because the university doesn't give it for home. So I can sign in. I will never have to do this again once I signed in. So it's an inward spiraling thing, and the X and Y component are shown here. And now we re-express the same thing using our MCRT, and we have the real and imaginary part of MCRT. The real, if you visualize this in the complex plane, so with a real axis and imaginary axis, what happens is exactly the same. Yeah, it's just what the only thing that essentially changes is the labeling of the axis and how the equation looks, but the dynamics is the same. It's just a 2D. It's two numbers that change over time. And previously these two numbers referred to the x and y component of Cartesian space, and now these two numbers refer to the real and the imaginary part of a complex number. Why do we have to deal with these complex numbers? So I think it has to do, but I'm actually not sure because this is, I didn't read about this in the books. I think it has to do just with the engineering business, so that It seems to be from an electrical circuit perspective and so on. It seems to be more natural to express 2D numbers as a complex number with a real and imaginary part. So when they built scanners and so on, they had these 2D signals. It made sense to put this into a complex and an imaginary channel, if you want, rather than to think about it from a Cartesian 2D perspective. And then, of course, it's also closely related to the complex exponential form of Fourier analysis. So this is also where this comes in. It's a mathematical thing, I would say. It doesn't change anything in terms of how the signal evolves and that it's a 2D entity. It's just that it's either described in Cartesian space using these cosine function, or it's in a sine function, or it's described in complex plane using complex exponentials. So let's have a break now if there are no current questions or other questions. No. Let's have a break now and then look in detail how or basically essentially where this equation here with the complex exponential, where this comes from. Yeah? Okay, let's have a break.